So today we have the class of the software engineering, but instead of that, I am engaging today's class of first operating system. Now, so far we have already discussed about the memory management, and in the same chapter, uh, I want to give idea about the paging and segmentation. So about the paging hardware, now you can see how the central processing unit have the connectivity with the page table and the physical memory. So here the physical memory, it is nothing but the random access memory. So whenever we will talk about the operating system and how the different processes are taking place, then it has the connectivity with the central processing unit, because first the program or your information or any process first processed in the central processing unit, and after that it has the interface with the physical memory, because the data will go to and fro from main memory to the central processing unit, and after the final settlement it will go to the secondary storage. So during the processing of any program, just there is a big role of the CPU and the main memory. So how the data is transferring from each other for the processing purpose, you can see here. Now the concept of the paging, whenever we are going to divide the memory spaces equally, then if we are going to divide the memory in the form of number of blocks, and if the block size is same, then we can say the paging. And in case of the segmentation, here the block size is different. Okay, as we are going to divide our memory into number of blocks, and if block size is same, then we can say the concept of the paging. And beside this, we can define the segmentation if the block size is dynamic or different. So the size of the block is not same, not equal. Now in this case, you can see CPU, central processing unit, it generates the logical address. Okay, so P here, it is indicating the paging, and this is the offset D. So it generates any process. If it is in the CPU, central processing unit, it will generate the logical address, and after this it will go towards the RAM, random access memory, where we will get the physical address. So we always divide this memory in the form of the physical address. Okay, so this generates the logical address, and after this generation of the logical address, the concept of the page table will start. So here we will get the logical address, and now in this case, the page table has the collection of the information and the number of pages in the page table. Okay, as we are going to divide the number of pages in the form of the blocks, so the storage will take place in the page table. So there is a always page table, and page table, this is divided into number of blocks, and after this, here you can see this logical address. So these are the number of pages here, and it is again go to the frame. This is F is the frame, and again this is the offset. So F and D, this is the P is the page, and F is the frame. So with the help of the page table, this information will go towards this side. And whenever we are talking in the context of the physical memory, then we always talk about the number of frames. So here is the number of pages. Okay, CPU here generating the number of pages here. So P and D, this is the offset value, and here the number of frames. So after this, here we will get the information from the page table, and it will go toward this side. So it will generate the physical address. So whenever we will talk about the physical address, then there is a concept of the frames. Okay, so after this, here we divide our RAM into number of spaces or the blocks, and that blocks may be equal in size or unequal in size. So we will define later on. But here you can see we will divide this space in the form of the hexadecimal addressing. Okay, so this is indicating the physical address. So whenever we will write or indicate here this side and this, okay, and up to this, so we can divide into number of frames here, and that may be again equal or not equal, and here we can write the address in the form of the hexadecimal code. Okay, so that address or space is called the physical address. So physical address is generated by the memory, that is the RAM, and logical address will be generated with the help of the CPU whenever the process will go inside the CPU, and the number of pages or the collection will take place in the page table. Okay, so this is the page table. Here number of pages here reside. Now what is the paging? Here we can calculate the internal fragmentation. Okay, whenever we will talk about the number of frames, okay, as we have seen in case of the RAM physical memory, here we are going to divide into the number of frames. Then how we will calculate the internal fragmentation? Okay, fragmentation means the part which is left after the occupation of number of processes inside the memory. So again, there are some spaces or the we can say the small holes or the parts which are left by the number of programs in the RAM or in the main memory. Then that left part here, we know that called the number of holes. Okay, then how we are going to calculate the that space? Okay, then that space is called the internal fragmentation. Okay, as we are going to combine all those holes, okay, that is called the coalescing holes. Then that space is called the internal fragmentation. Okay, so here suppose if we know the page size, just we are assuming that the page size is 2048. Okay, here bytes, and process size, that is your program size, is 72,766 bytes. Then we know that how many pages we are getting here. Okay, because the page size is this 2048. Now we can divide the process size or the program size by the page size. So just we are going to here, just we are assuming that the page size is 2048 bytes. Okay, now we can divide this process size by the page size. So as you will divide this, then you will get here 35 pages. Okay, now you can divide 72,766 by 2048 bytes. Okay, so you will get here 35 pages. Now only the 1086 bytes will be left here. So we can say that we are getting here 35 pages, okay, 35 pages plus this bytes, okay, 1086 means approximate half of the page, okay. Here you can see means 35.5 approximate, just we can say, or a little bit more than that, 35.5 pages. But in the form of the bytes, how can we write this 35 pages plus 1086 bytes? Okay, now internal fragmentation. How we are going to calculate the internal fragmentation? Then 2048, because this is the full size of the page. Okay, then 2048 minus 1086 means we have here 35 pages, but in that single page, how much our memory is going for the wastage here. So 2048 minus 1086. Okay. because this is half of the page occupied by the process, but remaining of the page, or we can say 1086, uh, mm, other than 1086 bytes, means whenever we will subtract, means 962 bytes equivalent to this space will go in vain, will go for the wastage. Okay, 962 bytes. So this is the wastage of the memory. Okay, because 35.5 pages, or in the last page we have still this space left. Okay, 962 bytes. Now you can see here. So this is called the internal fragmentation. This memory we can't use. Okay, this is the space left by our process. Okay, so 35 pages plus this and remaining bytes, remaining space left on the last page. This, so this will go in wastage. Okay. Now, so small frame size desirable. So we will try to reduce the size of the page, okay, here, or size of the frame. So, but increases the page table size. So if we will try to optimize the conditions, okay, so that we want to save the memory, we want to uh, this much space, or we want to save the wastage, so that we don't bear this type of memory, or we can say the wastage. Okay, so the frame size here, now the process or the method is we can increase the page table size. Okay, so whenever we will increase the page table size, is mean here we can say more number of bytes will be required, or it is equivalent to the page size. Okay, so whenever we will increase this size, it means the less number of pages are required. Okay, so but what will happen here? Poor disk input output. So a small frame size is desirable. Here we want to reduce the frame size. Okay, or if we will reduce this size, here the page table size will increase. Okay, and another impact you can see here, poor disk input output. Page size is growing over time. If we will increase, so the time will increase here, so page size is growing over time. So this is the system. Solaris supports two page size. Okay, two page sizes are 8 KB and 4 MB. Now you can see here in the Solaris system, it supports two type of page sizes. So either we can choose 8 KB size, or maximum size of the page is 4 MB. So it will depend on the type of the machine, which type of machine we are using. So it will depend on the operating system, what type of operating system we are using, and the page size will vary. Okay. So as per the variation of the page size, we can say that the wastage of the memory may be less or more. Okay. So here this wastage of the memory, just we are going to calculate, that is called the internal fragmentation, because we are going to combine all those holes which are left by the number of programs or the processes. Okay. So that space we will combine at the end, then that is called the internal fragmentation. So that is the big holes after combination of a small policing holes, then that is called the internal fragmentation here. So what is the user view and the physical memory? Now very different. User view, process contains in single contiguous memory space. So this is the user view. So the user which is using the operating system, then what is from the point of view of the user, he will feel like the process contains in single contiguous memory space. Okay, you will not say that how many pages occupied by your program or the process, because on the system. Just you can see on the screen that there are 1000 or 2000 or 5000 lines, but you cannot judge that how many pages are occupied by your programs. Okay, because you are not going to calculate the page size, you are not going to calculate the internal fragmentation. It will depend on the machine, on the operating system. So the wastage of the memory will vary as per the use of the machines. Okay, by type of operating system you are using. But the user always here will feel that our program or the process contains in a single contiguous memory space. Okay, you will feel that all the pages are collected and we are using only this much part of the memory. So that is called a single contiguous memory, because you are not going to judge how many pages are used by your program or the process. Okay, so this is called the user view and the physical memory. So that is the different, because we are using the physical memory. Okay, operating system, here managing all those things. Okay, calculating the internal fragmentation, calculating the number of pages or the page size. Okay, that will also depend on the type of the operating system or the machine. Okay, so all these things are managed by the operating system. So the user always will feel that just we are or our process occupying only such and such a number of or MBs, or we can say the bytes. Okay, because you will not say that I wrote the program and my program uh, is going to occupy 34 pages, because you are not aware by the number of pages or the size of the page inside the memory. Okay, so you will always talk in the context of the memory, that how so and so much memory occupied uh, okay by our program. Whenever you will check the properties, then you can say that our program occupy the 8 MBs or 4 MBs or like this. Okay, so you will always talk in the context of the memory. So by implementation, process can only access its own memory. Okay, so how we are going to protect that memory? So this will come under the paging concept. So this is the concept of the paging, how we are going to calculate the page size, or how we are going to calculate the internal fragmentation. So internal fragmentation is that there are number of processes which are running and occupying the different parts of the memory, and after that you have already checked here that the last page there are some space maybe left here, so that we cannot use for the another process. Okay, so those left part is called the holes. Okay, so after that at the end we will combine, or the operating system will combine all those parts, that is called the collision holes. Now here we can check each page table entry 4 bytes. Now we are going to divide the page table into number of blocks here in the form of the four bytes. Okay, because one bit here, 1 byte is equal to 8 bits, then 4 bytes 32 bits long. So each page table entry, okay, because we are just going to store some of the pages, or residing all those pages inside the page table. In the preceding slide, you have already seen uh, the diagram. Now, after the CPU, you can check again here, because it has the page table here. So all those pages are reside here. Okay, reside in the page table. So here we are going to divide the page table entry in the form of the 4 bytes. So it have means here 32 bits long. Okay, each entry can point to 2 to the power 32 page frames. So the number of page frames, how we are going to calculate the page frame? So 2 to the power 32. So it will depend on the number of bits. Okay, so what is the page table entry? So at the starting, just we are going to define the here page table entry size. This is we are going to fix 4 bytes here, and it will depend on the machine to machine. So if your machine is here 32 bits long, then the total number of page frames which we will get here for each entry, it is equal to 2 to the power 32. Okay, so this is called the page frames, and page frames we are going to calculate with the help of the page table. Okay, so if each frame here, each frame is 4 KB, okay, the system can address 2 to the power 44 bytes or the 16 TB of the physical memory. So up to how much we can address, so it will depend on the frame size here. So if each frame is 4 KB, then we will calculate in the form of the number of bytes, because this is kilobytes. We will convert into number of bytes, 4 into 1024. After that, we can calculate in the form of the bits. Okay, and after that, here we can say it can address up to 2 to the power 44 bytes or the 16 TB of the physical memory. So this is the in this form we can calculate the physical address also. Now here you can see process P1 arrives, requires n pages, so it will depend. Suppose you have only one process P1, so it will go to the CPU, central processing unit. Okay, and it may require n pages. So here just we are going to generalize, requires n pages means n frames must be available. So this is the size. So the size of the page here, just it is the minimum requirements. If there are n pages, means the n frames must be available for that. So if there is a one process P1, so it may contain n pages, and if there are n pages, then at least n frames must be available. Okay, so allocate n frames to the process P1. So the process P1 will allocate n frames. So create page table for P1. So for this process, first we will create the page table. So this is the process. Whenever the process will go inside the CPU, it will create the number of pages. Okay, number of pages. Just here we are uh, considering that there are n number of pages. It means n frames. Okay, so it will form the page table also for the process. So as the program will run, it will create a page table for a particular process or the program. Okay, so as the process or the program will go towards the will reach to the central processing unit, so it will create the number of pages, and it will also depend on the size of the program. Okay, so the information here it will store in the page table. Okay, so the CPU always create the page table here after process of the P1. Okay, so just we are here nomenclature, doing the nomenclature P1, P2, and P3, and so on. So just we are considering that this is the process P1. Okay, so n pages, there must be n frames. Okay, allocate n frames to the process P1. Now this process, first process, is we are allocating n frames to run this process. Okay, so as this process will run, it will create a page table. Okay, it will create a page table for P1. So this is the first program. It will create a page table, and after that, it has the connectivity with the RAM, because after creating the number of pages in the page table, the process will go toward the RAM, random access memory. Okay, now here you can consider which frames are here free or not. So again, like the number of pages, we have the page table. Similarly, we also have the frame table. Okay, so whenever we will talk about the frame or the frame table, just we are going to talk regarding the RAM, random access memory. Okay, because the CPU will generate the logical address, and after using the RAM, it will require the what type of address? Physical address. Okay, so there will be the frame table here, the free frame list. Now you can see here, and again it is divided into page 0, 1, 2, 3. Here new process. So it will depend on the size of the process, how much the size occupied by the new process here. Accordingly, the operating system will divide into the number of pages and also into number of frames. Okay, so CPU and the RAM, how they are going to connect, and whenever the process will run, then the page total number of pages will convert into the number of frames, occupy the uh, here number of frames. Now there are some few frames here are left, that is called the wastage of the memory. So now you can see here before allocation, now here this process is not going to allocate anything. This is the RAM free frames. These are called the free frames. Just we are talking in context of the random access memory. Okay, so this is the random access memory. Just here we are going to divide in the form of the number of frames. Okay, we are going to start 13, 14, 15. These are the spaces or the number of blocks. We are going to divide the RAM here into number of blocks. Here you can see, and these blocks are called the frames. And now how many frames are, we can say the free. Okay, now here we can see these all are the free frames because before allocation, it is not our process is not allocated here by this RAM, random access memory. We are not going to allocate this RAM. And now here you can see free frame list again, new process, page table. Okay, so as the process will run in the CPU, and this will form the page table. And after allocation, you have already seen that it has the connectivity with the number of frames after running the process in the CPU. Then here you can see these pages will go in the form of the frames. Here again there is a list of the here frame list. Okay, so after allocation, here you can see the situation. Okay, so page 1, 0, 2, 3 like this it will be occupied by the random access memory. So this is called the system view. Okay, now you can see here there are a few spaces again left here in the RAM. Okay, so page 1, page 0, and this is the random occupation here. The random space occupied by your process. Okay, inside the RAM here. Now you can see, so randomly here this is going to occupy. Okay, page 0, 1, 2, 3. And now these are the different parts here or spaces left. Okay, so we can call these frames as, because we are, if we are not going to use these number of pages, then this is called the internal fragmentation. If some space left inside the page. Okay, now you can see here page 01, and this frame again occupied by the number of page, but here we are not going to mention any in number of page here. Then we can say this is the wastage of the memory. Okay, here in the form of the frame. So this is the situation before allocation and after allocation. Now segmentation. In segmentation, here we can see in case of the paging, because the size, block size is same or equal. Okay, but in case of the segmentation, just we are using the memory as per requirement of our process. Okay, so we can also call this the dynamic allocation. Okay, here the wastage of the memory is less. But in case of that system, here as the operating system is going to calculate the number of pages for any process. Okay, then at the end you can calculate there are some space left that will go in vain. Okay, that is called the wastage of the memory. But in case of the segmentation, here we can say that the requirement is based on the dynamic process. Okay, so memory management is skill that supports user view of memory. Now again, we will see the diagram, and then you can differentiate between these two diagrams. Okay, in case of the paging and the segmentation. So here a program is a collection of segments. Okay, the process here we are going to use that is called the segmentation, and it will depend on the requirement of the memory. We are using those blocks dynamically, and just the operating system is going to reduce the size of the memory here, and also reducing the wastage of the memory. So we will always try, or we can say the operating system will try to follow this the method of the segmentation. Here we know already aware that a program is a collection of the segments. Okay, so a segment is a logical unit. So always whenever it will go inside the CPU, then we can say that a program is a collection of the segments. It is all right. A segment is a logical unit, okay, such as now this is the way to write any program. First is the main program, okay. So this is the procedure we can say to develop any program. For that is in the first phase, just we are going to write the main program, and after that procedure, and then function, then method. Okay, then object, local variables, just we are going to define global variables, all those variables which we are going to define above the program, and the value is not changing throughout the program. Okay, that are called the global variables, the local variables, those variables which we are going to define within the program, and the value may change. Okay, so the common block here after that is that will start the process, and then symbol table, then arrays. So this is the here we can say this is the methodology to write the program. So always here we will get a number of segments, and a segment is a logical unit. Okay, this is also called the logical unit, because after the writing of the program, it will go in the CPU for the processing, and it will create the logical address. Okay, so that is called the logical unit. And after the processing, we will get some number of pages, and after these number of pages will go to form the number of frames, and then those frames, the area that is occupied by the random access memory. Okay, so here how we can use this methodology. Now here you can also see the compiler generates the segments. Okay, so the compiler, whenever we are going to compile our program after writing this, so the compiler generate the segments. So it will divide it into number of parts and a number of segments, and after that loader assign the segments. Okay, loader loads your program. Okay, now here you can see the user view of a program. So what is the user view of a program? In what way we are just treating our program, or in what way we are here showing or indicating our program. So this is called the user view of the program. Here we are going to divide our program in the here. There are several ways, subroutines means some methods or procedures for the particular program which you are going to write, and then a step here. This is called the step. Is going to store the information related to your programs here. Symbol table. Again, there are some functions. Okay, which the operating system is going to store. Here the compiler will store the various functions here in the symbol table. Okay, about the length of the program, and also we are going to define number of variables. So the information about the number of tokens will store in the symbol table, and after that there are again because we use a number of header files, and if we are using the sqrt function or some other, and this is the main program. So how the program we are going to divide, so this is called the user view. Okay, this is not the system, or we can say the software view, but this is the user view. In what way the user is treating his program and going to divide this. So this is the way we can divide our program. So variable size segments without order. Now how we are going to divide our program. So variable size segments here, length, purpose of the program, elements are identified by object. Okay. So whenever we will write the program and if it is going in the CPU, then it will generate the logical address. So this is the primary stage. Okay, after writing the program, as it will go inside the CPU, so it will create the logical address here. Okay, so this is called the user view, how we are going to divide our program. So in this session, you can arrange or manage. Now I am going to take first your attendance here. Now any question about till now? Any question, Farhan or anybody else, please? And today I will try to engage my another class. Okay, at a particular time which is provided in your timetable.
सर मैंने जो सर असाइनमेंट मैंने सेंड किया था सर आपको कैसा था तो बता दीजिए सर।
कौन है, इरशाद साहब बोल रहे हैं क्या?
जी सर।
हाँ